great supervisor, obviously. Managed to lose his own student. He's lost his own student. said, my name's John Veitch. So I was invited by Ricardo to talk on a few different topics. I think this is a good one to start with. It's quite a broad area, so I can't cover everything in all the detail that it deserves in my presentation, but the time will be for discussion in order to dig into some of the details. So I'll try and go through a few different top-level subjects, so you have an idea of where things are at the moment. And also, I would like it if people can shout out with questions at any time. And if there are questions that require a long time to answer, then we can make a note of them on the board, because I would also like in the meeting to come up with a list of discussion topics that we can participate in throughout the couple of weeks. So if you have a question, we can write it down over here. And if there's any calculations and so on that we want to do, we can use the other board as well. So let me start just to explain what I'll say. This is only going to cover the first part of the session. The second part we'll devote to actually discussing things. So I'm going to tell you a little bit of the background of general relativity and tests of general relativity in the context of gravitational wave physics, what kind of things we can look for, how black holes are a good way of doing that, especially with the fact that they're the only gravitational wave sources that we've seen so far. So really we have no choice. But so there are current results, thankfully. Having given this talk a couple of years ago, it would be very different, but there will be some actual tests of GR from gravitational waves that we can talk about. And then looking forward, future prospects, in particular, what we will need in the future to dig into some of these different tests to a bit more in a bit more depth. I think also it would be good to talk about how we can use LISA as well as LIGO in particular, and maybe also pulsar timing arrays, but I think for reasons that I'll explain later, most of the really good action is going to be at the LISA and LIGO side rather than the pulsar timing array side. So hopefully that can stimulate a few areas to investigate over the next few days. So let me just start with a very broad overview of why do we want to test GR? Well, we're scientists, so we should be encouraged to test all of our theories. General relativity is 100 years old now, and it's passed every test that it's been subject to. However, it's not an easy theory to test, because gravity itself is quite a weak force, as you all know. So it's very well tested in an intermediate regime that's accessible to humans in the lab, and mostly through observations of astronomical phenomenon, ranging from solar system tests of GR, where we have a lot of our most precise measurements of the kind of static type behavior, out to cosmological scales. And then at very small scales, things are quite unknown. It's difficult to create phenomena that interact gravitationally on short ranges. So there are things like tests of the inverse square law that go down to the sort of centimeter scale, and possibilities of deviations from that on scales below centimeters down to millimeters, depending on whether you believe in some of the theories that predict large extra dimensions. And then at the top end, of course, there are observational results that suggest that general relativity alone is not the answer to all of our description of the cosmos. So, as you know, there are dark matter and dark energy have been introduced. The nature of these, well, dark matter has been fairly well constrained in terms of its proportion in the universe and so on. Dark energy, I think, is still a big unknown. But it's modelable in general relativity, but there are alternatives that can possibly explain the phenomenology as well. So I just illustrate this with the test from the binary pulsar. This is Kramer and Wax. I put references to many of the plots that I'm going to show. Hopefully, if people are interested in a particular area, then that's a good jumping off point to dig into the literature. So you can see here, this is it a pointer, by the way? A laser pointer. Well, you can see here, this is something that will show you a few different versions of plots like these, where you've got a sort of parameter space of some particular observation or of the theory. In this case, the binary pulsar, the mass of the two objects gives this plane, and then measuring different effects from so here you measure the delay of the light in arriving at the radio telescope, and you can pin down each of these measurements give you a different constraint in this mass plane, and if the theory is consistent, then they should all overlap in a single place. In this case, they do around here, and that gives you the mass of the two pulsars. And there are other plots I'll show you where you can sort of rule out different parts of, you can see that everything is consistent in this plane, or in a similar plane. Because you need to know the derivative of the orbital period. Yeah. So alone, I guess with only Newtonian dynamics, you wouldn't be able to actually infer this at all. Okay, so now we need to think about, well, we have a perfectly good theory of gravity as far as we know. What is there that we can explore around that theory? So I took this nice diagram from Berti paper, which is a very good review article, actually. I highly recommend this, but it does go into depth on some of the directions in which you could change the theory of gravity by relaxing different assumptions of the theory, adding additional fields, and so on. So it starts from this Lovelock theorem, which states that in 4 dimensions, subject to some suitable constraints, then general relativity is a unique theory of gravity up to, well, this cosmological constant term. And then by violating those different assumptions that go into satisfying or constructing this theorem, you can see how general relativity could be wrong. So you can either have extra dimensions, in which case there are different terms that could come in, different behavior on different scales. Then you have extra fields, for example, that's probably covering a lot of different phenomena, things that modify the overall behavior of the theory, and then additional dynamical fields, so additional degrees of freedom that can be then further subdivided into their propagation modes, scalar, vector, and tensor. And there's some zoology of different theories that live in this space of possible descriptions. I'm not a theorist, so I can't go into a huge amount of depth on these, but maybe Ricardo, I think probably, or Sathya would be able to say a bit more. So some of these things we can look for already with our gravitational wave observations, and I'll show you how we do that in a kind of generic way later on. So I think the point here is that when we're testing GR, we're trying to eventually test these assumptions that go into the construction of GR to see if there's any cracks in its armor where that might not be true. In particular, we're looking in the strong field behavior, and when I say strong field, This is kind of a relative term. As I'll explain later, it's not incredibly strong field, but it's still where we start to see sort of dynamical behavior and gravitational wave emission and so on. So what do I mean by that? Well, you can sort of plot different gravitational phenomena on this axis of the curvature scale of the phenomenon, and then the gravitational potential as well. So you can see, you know, up till now we have had solar system type constraints around here, and then down at the kind of low potential, that's Earth-based experiments. You have tests of the inverse square law, results from atom interferometry and studies of neutron behavior and so on. Then you have these kind of galactic scale phenomena as well that are much longer wavelength, you know, looking more at the cosmos, probing the very large. And then up here we start getting into the area where you have dynamical phenomena where the radiation reaction has an effect on the source. And you can see that advanced LIGO in particular is kind of sitting at the top in terms of what we can measure so far. And I'll show you kind of where our sources sit on this in a minute. There are also things like triple systems that might be very good if there were, you know, triple systems with pulsars, then it would give you another way of testing the doing these pulsar tests that would be even more stringent. Yeah. I don't think there are any with pulsars at the moment. Well, the weak equivalence principle and things like that, because then you have, especially if you have neutron star and white dwarf and so on. No, I think this is a possible thing, yeah. Yeah, I don't know what particular parameters you need to get up here, but I mean, there is a little arrow there that points things out. But I mean, I say it's a strong field. The potential is high for these advanced LIGO sources, but when you're looking at the curvature scale, the units here are kind of 10 to the minus 11 per square centimeter. And we're still very, very far away from anything that could be considered high energy in the terms of particle physics. If you don't believe that there's any physics between GR and the Planck scale is, you know, as far off the top of this plot. You know, you can see the range here is like 50 orders of magnitude, and then you need to go another 70 orders of magnitude off the top to get to the Planck scale. So there's a big question, like, is there actually any low curvature phenomena that we can measure with our astrophysical observations that would shed some light on whether there's any deviations at the very high energies where people expect that the theory must break down. But I think it's an unknown question or an unknown answer at the moment as to whether there is anything in that intermediate regime and how do we get there. Just looking at it another way, these are the astrophysical kind of systems. You've got your solar system tests down here, and the geodesy mission Lagios. I don't know how you pronounce it. Lagios. And then double pulsars. You go up here, and then I've added the LIGO sources onto this now. This is from the 01. You can see that these are not just points, but because they're evolving over time, they give you a kind of sweep through the parameter space of the constraints here. So you actually get a probe of how the movement happens as well. It's just whether a particular point satisfies the theory. It maps the gravitational field of the Earth, I think. You probably know some of the people involved, but the lens stirring effect is kind of a byproduct, isn't it? It was designed to measure the field of the Earth to look for variations in the ice melting and yeah. Yeah. Well, I don't see Gravity Probe B on here, so I don't know whether that's a different way of testing it, but we should probably look into how that works. And as I was saying at the start, pulsar timing arrays do have a place in this, but I think there you're looking at the very, very long timescale issue, so you're kind of constrained by the length of the observation that you can make and the time that these things evolve over. So that's why you're fairly low down on this axis, even though you're high up in potential. That's basically just looking at the same thing in a different way. So we'll probably skip over that. If you want to read more about these constraints, there's a UNIS reference there. So now we go now to gravitational waves. That's the main area of discussion for me. So for those who aren't familiar with gravitational waves, well, I hope you're all reasonably familiar with gravitational waves at this point, but these are, quadrupolar waves that are emitted by compact binaries and other phenomenon where you have a changing mass quadrupole. They're terrifically powerful because it takes a lot of energy to actually do anything to space-time, and that's one of the reasons it's so difficult to actually get a handle on them. So only the most disruptive type events, coalescence of binary black holes being the best one so far, of course, will actually produce a detectable signal. So even though the power of the source is something like 10 to the 46 watts or even more, I think, that's for a 2 solar mass system. So the ones that we've been seeing are another order of magnitude higher than that. They produce this terrifically weak strain that falls off as 1 over r. And so once you go roughly 10 to the 22 meters away from the source, which is kind of 100 megaparsec scale, then the actual size of the strain that you can see on the Earth is scaled down by this kind of 10 to the minus 22. So you need to produce a very sensitive experiment in order to detect them, and I'm sure you all know what LIGO is, this L-shaped device here that's designed especially because you pick up on the differential strain of the X and the Y arms caused by the gravitational wave, and that's read out in the interference pattern of the laser as it recombines and hits the beam splitter. The ones that we've detected so far, these binary black holes with LIGO, are in the kind of tens of hertz up to a kilohertz region, which just happens to be the sort of audio band, so you can hear representations of them very nicely. But then we're talking about gravitational waves across the spectrum, so when we go down to LISA and PTAs, we'll be heading down towards millihertz roughly for LISA, and then nanohertz for pulsar timing arrays. So these are with wavelengths that are comparable to kind of the extragalactic scale in the case of the PTAs. So these compact binaries that we've detected so far are both, or they're all from binary black holes. And you can look at the way the signal evolves over time. You've probably seen this famous plot from the detection paper. We can break the signal up into 3 rough phases. The in-spiral part, where the 2 objects are still well separated, and they're orbiting around each other, giving off gravitational radiation, which causes the orbit to collapse. Eventually, they'll reach within the last circular orbit, when the orbit can no longer be stable, and then they plunge inwards and form a highly perturbed black hole, which then gives off gravitational waves in the form of a ring down, which you can see is this exponentially damped part at the end of the signal, and settles down to form a kind of final Kerr body. And each of these phases is something that can be used to test general relativity. And I'll talk a bit about, in particular, what kind of tests we get from the in-spiral, what kind of tests we get from the ring down, and then what we can do by looking at the whole thing together as a kind of coherent type of source. In addition to tests of general relativity, of course, these waves tell you a lot about the system itself. So before you can get on to testing GR, you actually need to know what it is you're looking at. Otherwise, you wouldn't be able to tell whether there's some disagreement in the waveform that you see from the predicted waveform of GR. It depends on a bunch of parameters, which I will come to in a minute. Sorry, let me just go back. I should point out here that this velocity approaches kind of large fractions of the speed of light towards the end of the signal. So you're really measuring highly relativistic effects, and that's why these are a unique probe of GR, because there's nothing else that we have such good readout from in this kind of regime. So comparing the predicted waveforms to what we actually see is going to be the general philosophy for doing these tests of GR. And to do that, we actually need to know what waveforms we expect, and that's a big topic in its own right. So I should sort of just very briefly talk about this. The best way of getting these things is numerical relativity, where you solve Einstein's equations in full on a large grid, basically. You can take your binary black hole and evolve the last few orbits and see how the final coalescence and merger and ring down happens. Because of the computational cost of this problem, it's difficult to then work from large separations and evolve the thing all the way through. So you tend to need to stitch your numerical relativity solution onto an analytic solution or another approximate solution that can be derived from the theory in the point particle limit. So when the separation is very large, it doesn't matter so much the higher order modes of the higher order moments of the system. And so the best waveforms that we have are created by taking one of these analytic waveforms, either phenomenological, which is usually described in terms of a series, or the effective one-body formalism. Well, it's also described in terms of series, but it's a different way of treating the problem. And then calibrating the end of the waveform, so they typically give out like around here. Then you need to have some phenomenological fit to how this behaves through the merger stage. I'll talk about how that's done in a minute. And then you add the ring down at the end. The ring down waveform is fairly simple, but it requires several coefficients to know how each of the modes in the ring down behaves and how that's related to the initial parameters of the source. So really what I want to do is I give a pair of masses, M1 and M2, a pair of spin vectors, and a separation, an initial separation, and then predict exactly what the waveform comes out as. So the waveforms that we've been using at the moment in LIGO for most of our tests don't actually capture everything that we could. We know that they're not perfect, and we know that there are effects of spin coupling in particular that are not treated in those waveforms. How the merger is described is pretty much phenomenological, and the effect of higher harmonics, by which I mean, the modes other than the L equals 2 mode of the signal are absent in most of the waveform approximants that we use to do our tests of GR and our parameter estimation. But in the subject to these constraints, we're still able to do a good job, especially when the masses are roughly equal and the higher harmonics are not so important, especially when the system is viewed face on, because there you have the dominant L equals 2 mode is producing most of the detectable signal, and the higher modes are not so relevant. So we're, so far with the type of sources that we've seen, we're pretty confident that the waveforms are good enough to do tests of GR, and I guess that's borne out partly in the results that we've got so far in tests of GR, which show there's no deviation, spoiler alert. One of the questions that I'd like to talk about later is like where these approximations are no longer valid, and what we might do in that case to mitigate that effect, whether we need better models to begin with, or whether we can take a more generic approach to the modeling, which ties in a bit to the sort of Gaussian process stuff that we'll talk about later in the week. So I would put that down as a question. It's already in my mind, but hopefully people will have a think about that as well. How are we doing for time? Okay, so that's GR. And then we have to go beyond that to actually look at the particular theories that we're interested in testing. And as I showed you, there's a big parameter space of different possible theories there. And all the work that's been done in numerical relativity for GR has largely not been done in most of these different theories, especially ones that have extra fields and so on. It becomes difficult to separate the problem in a way that can be done. And then you have to choose, of course, a particular theory to simulate, and the cost of these simulations is enormous. It's like thousands of CPU months to get one waveform. So picking a particular theory and a particular set of parameters for the physical parameters and the additional fields and so on, you've got a huge parameter space to explore, so it's difficult to come up with a very accurate model. So what we will do, as I'll show you later, is come up with a kind of phenomenological way of describing the waveforms around the general relativity one. So the different ways that can happen, you can have alterations in the behavior of the source. That's kind of looking at the strong field and the dynamics, where extra fields, higher order terms in Lagrangian will come in. It's probably unlikely we'd be able to see things like that directly with LIGO, but there may be kind of low energy limits that we can pick up on. In terms of the dynamics of the source, well, we're pretty much relying on post-Newtonian or post-Einsteinian description of the waveform, and I'll show you what that looks like in a minute. Then there's the propagation of the waves themselves. If the graviton, or the predicted graviton, has a mass, then the waves will not travel at the speed of light, and that will actually accumulate over the propagation and lead to a difference in the phase when they arrive at LIGO. And then you have looking at the final objects themselves, and I think it's not so much a test of GR, well, it is a test of GR, but it's a sort of studying black holes in their own right, because we now have direct access to looking at these things as they ring down in particular, and it's almost like doing spectroscopy with atoms. You can start to look at the oscillations of black holes, see whether they agree with the predictions of general relativity or whether there's anything that's unexpected in the signals that we see. And that is something that's probably going to be a big deal in the future when we start to get sources with a much higher signal to noise ratio, where measuring different modes of the ring down becomes easier. So there's a lot of different things that we can get into here, and I can't really go into all of them in a lot of depth. I'm probably not even the right person to go into most of them in a lot of depth, but we can discuss some of these ways of getting at tests of GR amongst ourselves. So just going on to the analysis now, I'll talk a bit more about this later in the week, but just so you know the kind of scale of the situation, the vanilla GR waveform has 15 parameters. The masses, the time of coalescence, 2 spin vectors in 3-dimensional space, the distance, the right ascension, declination, inclination angle, polarization angle, and phase. And once you've set all of these, then you have a vanilla binary black hole sitting at a particular point in space and oriented in a particular direction. To go beyond that, you need to introduce a whole set of other parameters depending on the type of theory that you're interested in. So you're looking at a very large parameter space to explore in order to actually measure what you want to know on those parameters. We ignore most of these in our searches for gravitational waves. You can use nice tricks to reduce the dimensionality of the problem down to really just these first few. But then in the parameter estimation and tests of general relativity, we actually are interested in all of these things, and we need to know how accurately we can measure them. So it's important to actually explore all of this, and doing that in itself is a difficult problem that we'll talk about later in the week. But just very basically, the kind of philosophy that we take is this Bayesian inference, which some of you may be familiar with already. The idea here, just starting at the bottom, if these parameters are given by theta, which is kind of a vector of all the different parameters, and we are given some data d and a hypothesis gr in this case, that gr is correct, then we want to know what is our probability density function. That is the probability that the source really had those particular values of the parameters at one particular point in theta vector space. Given the data, well, you can use Bayes' theorem to write down your prior probability for those parameters. Then you have the likelihood of data at a particular fixed choice of parameters. And finally, this normalization constant called the evidence that becomes important when you're doing model selection. And we can talk about that later. This likelihood itself is kind of important because this is our model of how the instrument itself behaves, or how the noise from the instrument looks. We use this Gaussian description of the noise in the frequency domain such that there's no correlation between adjacent frequency bins in the limit of very long observation times. That's correct. But the autocorrelation of the frequencies is given by this power spectral density. That's these noise curves that you see for LIGO and for LISA. It looks something like that. So that's S, which is the power, the noise power in a single frequency bin. And the lower it is, the better, because then you have a lower uncertainty on the data point in that bin. And so you can measure most accurately when this curve is low. So the sort of units here are kind of 10 hertz up to about 100 hertz. You have the most sensitive part of the noise curve, and then things start going up again up to sort of 1 kilohertz. I probably should have had a slide with this on it, but a typical in-spiral source, when it's coming in, will leave a trace that looks like this. If this is the power in the noise, then this is the power in the source. So I'll put S of X for the noise and S of H for the source. There's this long power law component of the power, which is the in-spiral. So that spans many seconds to minutes and even longer in LISA. And then at the end, you have a very tiny little bump, and that's the ring down. So a lot of information is packed into this part at the end, but it's difficult to access, especially for lighter weight black holes, because the lighter the source, this moves this curve to the right, and this tends to get buried in the noise at high frequencies. Okay, so I've put examples here just looking at the vanilla GR parameters, that's the masses and the sky position. But these density functions that I'm talking about, this is what these are. It's a density in the kind of 15-dimensional parameter space, so you have to then integrate out the other parameters if you just want to look at two of them in particular, for example, the masses or the sky position. So you can't really visualize the full distribution, but you can get an idea of the kind of shapes that you'll get. And I'll talk a bit more about that later in the week. So the first tests of GR I'm going to talk about are these parameterized tests. And these are kind of the simplest ones to explain because they use GR as a kind of starting point and then just phenomenologically perturb the GR signal in a different way. And then you can set bounds on how the deviations from the signal can look at different parts of the, well, I should say different parts, but what I really mean is different components of the signal. So you break this h of f in the frequency domain into an amplitude and a phase term. So you've got a of f and phi of f. They depend on the GR parameters theta. But then for each choice of theta, say M1, M2, and the spins are the only ones that are relevant in the phase, then you can write this phase as a post-Newtonian series. In the case of phenomenological waveforms, the intermediate part between the merge and the ring down is also described as a power series where there are just different functions g that aren't so, related to the frequency and different coefficients there. So in the post-Newtonian area, each of these powers of frequency has a different coefficient given by phi here, or psi. So what we do is we just take the GR value of psi and add on a multiplicative deviation delta psi for each of these orders. So this is a kind of very generic way of changing the waveform, motivated by any particular theory, but it does capture quite a lot of different effects from some of these theories. So these are the extra parameters of these delta psi's. And if they were all equal to 0, then you have exactly your GR waveform. You can vary them all at once, or you can vary them individually, and depending on how you do it, you get different accuracy of the result. But the general philosophy is that this is kind of a generic test of GR. It's not going to give you a result on a particular theory, but it will give you some idea of how accurately you might be able to measure that. So looking at the constraints that we got from the first detection, GW 150914. These are the PN orders. The post-Newtonian series here starts at 0 PN when this is minus 5/3 and then proceeds upwards from there in higher powers of frequency, and therefore higher weights at the top end of the noise curve become more difficult to measure because the effects only come in later on. So looking at the results here, you can see a comparison between GW 15914 constraints on the post-Newtonian deviations away from GR versus what was previously the most accurate test was the binary pulsar J0737. So you can see, like, starting at 0 PN and going upwards, there's definitely a pattern for the pulsar in particular. We have a constraint of that's actually lower than that came from the gravitational wave. And as you go up in the PN order, this higher frequency becomes more important. And because the pulsar is varying its orbit much more slowly than the black hole binary, these effects become very difficult to measure. So there is a constraint, there's a reasonable constraint at 0.5 and 1 PN. I mean, something that I can show in this plot. At higher orders than that, they're basically meaningless, I think, the values that you can get out of these things. So I would say that with gravitational wave from black hole binaries are the only way that you can actually put constraints on these high PN deviations of GR, which is where you may expect to see some difference Well, it depends on the theory, which order will be modified. So the reason that the GW5914 is very good at kind of all PN orders, well, all the ones that we know how to measure, is that it spans through multiple frequency ranges and the velocities going up, towards the speed of light. I should have pointed out that the Taylor expansion for the PN series in frequency is also related to the Taylor expansion in terms of the velocity. So you use kind of V over C as a parameter to expand in. So you need something where V over C becomes close to 1 in order to constrain the higher orders. And the pulsar is not moving very close to the speed of light, but the black holes themselves scan through this region all the way up to kind of V over C is 0.5 or so. So if you go down to lower orders, then you benefit from very long observation times. So things like the binary pulsar, which you can observe over many years, will give you a much more accurate test than a gravitational wave that lasts less than a second. So the fact that even there is any constraint here that's comparable, even though it's about an order of magnitude worse, it's kind of impressive that there is a decent constraint here. If we measured sources that were longer in time and spend longer at lower frequencies, then these constraints would get better as well. So you kind of, I think we could talk about different ways of probing different parts of this space of deviations from GR. This is, again, a kind of taxonomy of different theories and how they fit into this post-Newtonian scheme. So I'm not going to go through all of these in detail, but we can maybe refer back to it if we're interested in a particular area. This again from the Eunice paper, and I guess the slides will be available for people can go and look at this, look this up and find all the references. But you can see that the different particular theories can be sort of cast into this framework of post-Newtonian deviations, and they are expected to show up at different post-Newtonian orders. So things like scalar and dipole radiation will show up at negative post-Newtonian orders, which means that they have a very large effect on the waveform, whereas things that go to higher post-Newtonian orders become more difficult to measure because they require a higher velocity and the source spends a shorter amount of time at that velocity. So that in general, things get more difficult as you go to higher post-Newtonian order. Well, that's correct, but the reason that the tensor radiation is affected is that you can think if you have a dipole radiation, that's going to be more effective at extracting energy from the source than the quadrupole is. So you will see a change in the binding energy that changes faster than you would expect if it was only gravitational waves that were being emitted, or if only the GR version of gravitational waves were being emitted. So if you see some kind of unexpected change in the orbit, then that could be due to dipole radiation, for example. So there will be some actual dipole radiation, but that is not what we're looking for. We're just looking for the effect that that has on the gravitational waves. But you might want to look for that as well. Yeah. Yeah. Well, actually, you can look for them. Yeah. Well, the problem there is that the LIGO detectors are kind of specifically designed to look for tensor modes. I actually have a slide on this. It might even be the next slide. These are the different modes. Okay, we're skipping way ahead. So this is the vector of propagation. So that's the scalar breathing mode. Yeah. But yeah. Well, yeah, that's right. So there's a neat thing you can do with pulsar timing. You can think of the Earth as being the vertex, and then each of the pulsars is an arm. And there's no limit, on the number of pulsars that you can have. So the more pulsars you add, typically it will give you a better detection or a localization of the source or whatever. But you can actually rewrite this in terms of measuring the metric directly at the Earth. So the perturbation around flat space at the Earth can be parameterized in terms of these modes. And then you can write down the relationship between each of these modes and the effect on sections of the pulsar. And you'll see that different linear combinations of these pulsar time delays will let you pick up different parts of the possible signals. So this is one of the things, actually was working with a student in Birmingham on this a little bit. So the first thing to do is just with GR is try and isolate the quadrupolar modes, and then you have these two H plus and H cross parts of the signal, and then so you need basically two pulsars to actually get that 2 degrees of freedom. Then you can keep adding more pulsars and construct null streams, as they're called in LISA, and because there's no limit in the number of pulsars you have, there's no limit in the number of null streams you have either. So you can look for any kind of effect that is not due to the gravitational wave. It should show up in the null stream as well, rather than in the H plus and H cross parts. Yeah. It's all linear algebra, isn't it? No, I was actually interested in doing that beyond the GR case. So you have an additional, you've got the kind of non-propagating degrees of freedom that you have to worry about, first of all. Oh, this is like the surfing effect or whatever it's called. Okay. Yeah, I'll have to get. Did you write it up already? Yeah. Well, I need to get the reference for that. Yeah, that doesn't surprise me. Yeah. So people have computed the response functions for all these modes for LIGO. Yeah. So that is the kind of that's quite generic. You don't need compact binaries to do that. The way that we do it with compact binaries is looking for anomalous energy being dumped into these additional degrees of freedom that change the orbit, basically. It's the same as the tidal deformation. It takes energy out of the orbit, and so it changes the way that the phasing works for the GR signal away from the point particle. It depends on the theory. So, yeah. That's why continuous waves, people are interested in this. Because you don't just have, a few seconds worth of signal to look at. You have F plus and F cross and F breathing and F longitudinal over a long period of time. So you can sort of break the degeneracy in the response by looking at how it changes over the Earth's orbit and so on. So that, I haven't put anything about that at all in the slides, but we should talk about that as well. Yeah. Now, I'm very interested in this PTA business and the kind of how you would actually go about detecting these extra polarization. Because something that's not even clear to me, in order to fix the gauge, to get the, you want to work in the transverse traceless gauge, that requires a Lorentz transformation to get there. And so you have these additional degrees of freedom to transform you out of the transverse traceless gauge. Yeah, and why there are, maximum 6. Okay. I'll put down continuous waves, alternative polarizations as well. Yeah, yeah. Indeed. Okay, so that's getting ahead of ourselves. Well, it doesn't really matter what order we go through this in, but I think we were just around about here. So, do we want to talk more about these particular theories? I don't know the physics of all of them. Well, some of them have pretty crazy names. Mm. Yeah, I mean, hands up if you believe GR is wrong at our scales. I'm not sure anyone really does, but it's got to be tested. Well, the tidal effect is a matter effect, so it's not, I mean, it's, GR is wrong in the sense that it doesn't describe matter at all. So it's yeah, so I think, I don't remember what slide it was, it's probably how, so your black hole solution, if GR is right, then these things that are 30 solar masses have to be black holes, basically. But if it's not right, then there could be boson stars, okay, probably not at 30 solar masses, but maybe up to sort of 5 or above. Then there could be other exotic objects like, I don't really know the details, but firewalls that maybe change the way the horizon works, and this, you know, this echoes paper that people have been talking about. Yeah. I think we should be doing that anyway. If we start seeing sources in the range of 2 solar masses to 3 solar masses, we don't know when it has to be a black hole or whether it's a neutron star. So there's probably quite a useful to develop a robust test for that. Yeah. It depends on where the coupling comes in the waveform, I think. Yeah. Yeah, yeah. That's one of the difficult things is because, as I'll say later on, if you expect to have the same equation of state in every neutron star, then by measuring lots of neutron stars, you can learn about that equation of state. But there's no reason to think that you have the same spin in every black hole. So it's going to be difficult to think, you know, of a test that lets you get enough sensitivity to measure that. Certainly with LIGO. Maybe with LISA it's more likely because you have a longer source. But I'm going to maybe put down black hole versus matter / exotic. That's something that we can maybe go into. Shall I continue? Yeah. So you want to know what you actually ought to work on with the effective field. Yeah. Uh, so here's a problem. I don't know how you've probably spoken about this with us, but if you look at this PN series, where are we sitting at the moment? We've got 4 PN for some parts of the waveform, and not for all of the spin terms, right? Yeah. But I think 3.5 is kind of where we will next have everything. And then we get to 4pn, and at 4pn, f to the 8 minus 5 over 3 is just f. And a change in the frequency, if the power law is f, it's completely degenerate with a shift in time. So there's no way that you can constrain any of the 4pn terms from gravitational wave observations. Because if you time shift something in the frequency domain, if I have h of f and I want to go to do a time shift, and it just goes to h of f e to the 2 pi I f delta t, right? So this power law in f is completely degenerate with the 4pn terms, apart from the logarithmic part. So I think the prospects for doing anything at 4pn are terrible. And I don't know what parts of the spin. So I guess one thing that could affect that is if the spin interaction depends on the velocity itself. So if it has a different coefficient at different parts of the orbit, so these things become functions of frequency as well, right? So it's like the precession term, for example. So that could break that degeneracy. But just the constant parts seems impossible to measure these to me. Yeah. 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 I mean, presumably the same applies for all of these, right? 7pn. It's meaningless to even talk about that. Yeah. Yeah. Okay. So PN constraints. These are the bounds. I showed you the bounds from 5914. I just wanted to point out that different types of, even just talking about LIGO, different types of sources will help in different areas. So you can see that if you compare 15914 with 151226, then you can see that sometimes 15914 wins, and sometimes 151226 wins. And that's basically due to the much longer waveform for 151226. The masses here were lower. So the lower PN orders, you get better constraints there. Sorry, no, it's the other way around. Yeah. This is just another way of looking at the same thing, but yeah, exactly. So this one is not centered at 0, in fact. However, you know, it's not really excluding 0 at a very high significance, but they do kind of jump around due to noise. Yeah. Yeah. I think there's another slide that kind of illustrates that. So I should just maybe skip over. This is similar looking results for the most recent detection, 170104. And again, this kind of sits in between 15914 and 151226 in terms of the mass. So the constraints that you get, again, are as you would expect from a source that lies in this region. Okay, so I put down a few discussion topics that we've already started discussing, so I'll just move over them. I think one thing is more of a kind of practical detail that we may need to be worried about is, so far, okay, with the exception of things like this, our results have tended to agree with GR to a good level. But even if we did see something that wasn't centered on 0, it's actually going to be difficult to convince ourselves that it's because of a violation of GR rather than a violation of one of these approximations that goes into the waveform. So we probably ought to do some work in exploring where this will break down in terms of the importance of higher harmonics, the importance of spins in the waveform that aren't modeled, and things like, if we view it from edge on, then the higher harmonics are more important. The effective precession of the orbit is more important, and so on. So these tests in themselves, although they've served us quite well, I think that they will break down at some point when we start seeing things that aren't equal mass binary black holes. Okay, so we've got only half an hour left. Remember, I was breaking up the signal into in-spiral, then there's a merger and the ring down. I don't know why this isn't just merger in the middle and then ring down here, but there's basically 3 phases. So another way of testing GR is to just split the waveform into 2 and see whether the 2 parts are consistent with each other. Because you know that in general relativity, only the masses and the spins of the progenitors, the 2 bodies, and then the final body affect the waveform. And there are good fits between the initial and the final masses and spins coming from numerical relativity now. So if you use these fits, you can sort of ask the question, if I look only at the in-spiral, what are the masses that I have? And if I look only at the ring down, what are the masses that I have? And if the theory is, if the waveform is consistent with GR, then it's self-consistent as well. And so you expect that the results that you would get from that would agree with each other. So we did that in terms of the mass and the spin. It's easier to write it in terms of the final mass and the final spin because those are the dominant parameters for the ring down part of the source. Whereas for the in-spiral, it's more the chirp mass and the spin, but then you can convert them into each other. If you do that, then you get these kind of dashed lines just looking only at the in-spiral or only at the post-in-spiral, that's the merger and the ring down part. And you can see that indeed they do overlap in a region round about here, which is consistent with the results that we've always quoted, that the final object was around 62 solar masses with a spin of 0.65 or something like that. So the full fit to in-spiral merger and ring down gives you this blob, and it's not surprising that these two things intersect in the place where that lives. So another way of looking at that is if you take the difference between the result from the in-spiral and the result from the post-in-spiral and divide by, well, you can choose either that one or that one, then you get this sort of delta A and delta M. That's the difference in the mass that you infer from different parts of the signal. So if GR is correct, then they must be the same. And so if you do that, you can get this density, probability density, which has a peak that, the 90% contour certainly contains GR, and even the sort of maximally dense area is pretty close to GR. So I think this is a null result as well, but it's interesting, the shape of this thing. Yeah. It is 90%. The contour. I think it's just because the volume here is bigger, so if you integrate this larger area, then there must be 10% of the probability outside. Probably. I don't see it. Well, moving on. We repeated the same test with the 170104, and of course, you get again the result that's consistent with the GR. In fact, it's even better, I think, it's within the contour here. Okay, so consistency tests. The final part of the signal is the ring down. So there are a range of different things that you can do with the ring down in itself. As people probably aware, the final black hole, when it forms, is not a perfectly spherical or a Kerr black hole in itself. It's going to be some kind of peanut shape, presumably with the two things joining together. I don't know how you can really assign a shape to an object that doesn't have a surface, but you know what I mean. And then gradually this emits radiation and settles down into a more spherical state. So the radiation that it gives off can be written as the sum of quasi-normal mode oscillations of the field around this object. This is all coming out of the Lever paper, and then there's a couple of good review. Bertie's paper goes into some detail as well. So you can write this as the sum of basically a bunch of ring down signals that's decaying sinusoids. Each of them has, I should say that the L, the M, and the N are the kind of spherical or the spin-weighted spherical harmonic overtone. Spin-weighted spherical harmonics L and M, and then the overtone index N. So there's a field decomposition in the exterior region, and then each of those has a complex frequency, which you can write as omega as the real part and tau being the decay constant, and a phase. So the phase in itself is not very interesting. As far as I know, there's no theory that predicts exactly how the phases of these excitations should look for a generic merger. It would be interesting to know if people have an intuition for how that should work. Like if, for example, you have a head-on collision, I would imagine that probably they're all aligned in phase when it starts. So what you're doing is looking at the omegas and the taus in order to do your test of GR. So according to, well, the no-hair hypothesis, well, I should just say, this is what the signal looks like for the ring down. It's a superposition of modes. Ditto in power here, so you get this kind of structure where you'd hope to be able to pick up the oscillations. So these two things, omega and tau, are theoretically speaking only functions of the mass and the spin of the final object. Once it's reached that sort of perturbative regime, so there'll be the merger, which is more dynamical, and eventually it will settle down so that all the modes should be related to this. So there's 2 degrees of freedom, the mass and the spin. If you measure more than 2 of these quantities, then you can relate it back to the mass and the spin and see whether they agree in terms of, you know, the prediction of those two things. If GR is correct, again, you're looking for consistency. So for 150914, I'm talking mostly about 150914 here because it's the loudest one. The black hole ring downs are quite difficult to detect because they're so short and they're quite high frequency. For 150914, we were able to measure a single mode of the ring down, which gave us this consistency with the in spiral. There's a few technical issues in how you do that, mostly related to when you pick the start time of the ring down. So if I go back just to this red line here, uses division here, but then the ring down part is really when this has reached a stationary frequency. So it's difficult to know exactly when that happens. You can't, well, can you learn it from the data itself? Can you learn it from numerical relativity simulations? Is it the same for all of the modes? I don't know whether all the modes reach their perturbative regime at the same time or not. That's something that would be very useful to know in doing this analysis. But for a single mode at least, depending on when you start this analysis, you can end up with contours that get larger and larger as time goes on, because less of the signal, you know, the exponential decay of the signal power means that the constraints get worse and worse as time goes on, even though you're probably more safely into the perturbative regime. So this is something that's been explored in quite a few papers, looking at not just LIGO, but Einstein telescope, LISA as well. So the one that I've been involved in with Safia is this Gossan et al. Paper. This is exactly what we did. It's similar to the binary pulsar test. We measure 3 of the modes. This is the GR case, and you see that if you measure 1 of the modes, you get a stripe in this parameter space of the mass and the spin. And if GR is correct, then they should all cross at some point in the parameter space. If GR is wrong, then you will see that there is no single point where they're all crossing, and so there's no self-consistent solution for all of these things in the no-hair theorem test. There are other ways of doing that using model selection that are gone into in this paper, but I don't want to get into the details here. You can also sort of combine multiple events to amplify the effect as well. Yeah. Well, I don't. I think you can. There's 2 other parameters, the amplitude and the phase. And I think these are highly dependent on the situation of the merger, so the geometry of the merger. Because if the phase sort of describes roughly the axis of symmetry, I would imagine, like the L equals 2 mode is clearly going to be preferentially aligned in that direction, but likewise with the amplitude of the modes, it would depend on exactly how the merger happens. So I don't know. I mean, you're working in ring downs, right? So Is there a is there a prescription that will tell you that? Even in the head-on case, maybe it's simpler. But it's based on the geometry, right? Yeah. For the amplitudes. For the amplitudes. Yeah. Yeah. But there's a tau, and the omega gives you the complex frequency, but the phase as well. This should be. This is a free parameter. But it could contain physics information as well. Yeah. Yeah. I think it's. Well, you can measure it for 150914. I mean, if you analyze 150914, you can get the amplitude and the phase for the 2-2 mode. But it's just a nuisance parameter, right? It's not giving you the tests of GR, but yeah. Yeah, there's I mean, the start time itself could in principle be different for different modes. I put just a single T0 here. But again, like, you have to choose when it's safe to say that it is a damped sinusoid. Okay. Just to before we move on, so I think that actually this isn't just about testing GR. You can get lots of tests of GR out of it in the same way that studying atomic spectra will tell you about quantum field theory in the atom. But I think it's actually what we should be thinking about is this is studying black holes for the first time directly from their excitations. So it's interesting in its own right, even if you believe that GR is correct and you're not interested in alternatives, to check whether you know, all these things agree with each other and whether they behave in the way that you would expect. Okay, so finally, well, maybe not finally, but propagation effects. I talked a bit about the how these. No, I didn't actually. So the first one to talk about is massive graviton. So this, in general, all these propagation effects take you off shell in your gravitational propagation, and therefore you get a different dispersion relation than you would in general relativity, or if it travels at the speed of light. And that basically means that gravitational waves with different frequencies will travel at different speeds through a vacuum. And so, in particular for sources like our chirps or in spirals, where they're scanning across different frequencies, you should be able to pick that up because it will differentially change the delay in the arrival of the gravitons from each of the different parts of the signal. In particular, it means that the higher frequency parts will travel faster than the lower frequency parts. So in the very extreme case, you may even see the signal reversed in time, if you like, because it will take longer for the low frequency parts to arrive than the high frequency parts. So this gives you a very good way of constraining the mass of the graviton, because we have very good phasing information about these signals. So we did this with 15914 and also with 151226 and 170104. Just with 15914, because it's so loud, the constraint that we were able to get, kind of 90% uncertainty, or 90% lower limit on this lambda g parameter, which is the Compton wavelength. I think it's more useful to talk about the mass. This is already better than the solar system bounds and those from the binary pulsar, so we're winning here, and that's mostly because our source is at very large distance. So there's a long time for the dispersion to pick up as it propagates over the sort of 500 megaparsecs or so. So the constraint that we set was roughly 1 times 10 to the minus 22 EV over c squared, which is better than the constraint on the mass of the photon, just to give you an idea of how this is. And we've had hundreds of years to try and measure the mass of the photon. The problem is that light interacts with matter. So as it propagates over astronomical distances, it does tend to get dispersed by the plasma in the universe. But that doesn't happen for gravitational waves. So we already get very good constraints from 15914, and they're getting even better as we detect more signals with a higher bandwidth. So I like this one. I think it's a nice example to go through in how to work out what the phase should be and so on. But I'm not actually going to do that. More generally, the propagation effects can be written in terms of this dispersion relation, not just for the massive graviton model, but if you pick a different powers of the momentum alpha, then you can translate those into bounds on the amplitude of this thing, which just corresponds to the mass in this case. And here you see, again, it's similar to the post-Newtonian where we've got different indices. Here we've got different indices on the alpha parameter. and different theories will translate to different alpha indices. So again, this is kind of a generic test where we then want to go back and translate the results into specific theories. I'm just outlining a few of them here. I'm not going to tell you the details about them. But this is basically the only way that we have of constraining these dispersion relations at higher order especially. The massive graviton can be constrained from looking at dynamics of galaxy clusters, and that'll give you a bound that's actually better than the one from LIGO, although it does kind of depend on your assumptions about dark matter and the energy content of the galaxies and so on, whether this is kind of a direct measurement. But then if you go up above 2, then the constraints that you get from that method are not so good, and the gravitational waves is basically the only way of doing well there. So that's just another handle on another range of effects. There are other ones I haven't mentioned here, like biometric gravity and so on. There's a big literature on how these map into differences in alpha. Okay, so I'm basically going through the last few things that are on the horizon. The dispersion relation being one that I expect will improve, especially when we get LISA in the picture as well as LIGO. Non-GR polarizations, well, we talked about these. I think that's a good one to investigate more this week. So the picture looking forward, in the near term, we have upcoming runs of LIGO. Well, it's currently in its second observing run. That's going to last until the end of August. But Virgo is coming online, advanced Virgo, as of tomorrow, I think, officially joining the run. So our ground-based network is getting better, and it's getting more sensitive over time as well. And that sensitivity improvement is going to translate into a higher signal-to-noise ratio and a more precise constraint on lots of these effects that we've seen. So not just higher SNRs, but we'll get more detections too. And the more detections we have, the better we can multiply the information together. And as long as we can cast our results in a common framework, then we should be able to come at it with multiple sources as well. Looking a bit farther forward, there's LISA as well. One of the nice things that was pointed out by Alberto Cesana was that lots of these LIGO black holes, as I would claim them to be with my LIGO t-shirt on, are also visible in LISA much earlier in their life. Well, the time it takes to go between the LISA observation when they're kind of at the tens of millihertz region up to LIGO is anywhere between, years, 1 to 10 years, depending on the mass. So if we have LISA going on, we can actually measure the chirp mass of these things using LISA and predict when they will appear in the ground-based detector with a very good accuracy. And if there's any difference in either the propagation due to dispersion or energy as a function of frequency due to the presence of additional fields or something like that, then that will change the time of arrival of the coalescence in LIGO. So over this time scale, it's not so much the frequency range that helps, it's the time it takes to go from LISA to LIGO. If you can measure that, as you will be able to, you'll get a really tremendous test of general relativity, because you'll have to check that it will coalesce at the time that GR says it will, and not at the time that it would if there was additional fields or tidal effects or so on.
Yeah, about this.
You're going to tell me it's all rubbish?
No, absolutely not. But there is a recent paper showing that actually if you want to get that precision, the precision of predicting the time of arrival to minutes, actually you get into trouble with the peculiar velocity of the sources. The peculiar velocity
Ah,
and jitter
yeah.
can give you an uncertainty in the parameters you measure from LISA that can affect, I mean, if you want to extrapolate the time of arrival in the LIGO band months or years afterwards, then you can get minutes error.
No, well,
minutes won't be ascribable immediately to the deviation from VR,
okay.
but there might be a statistical effect that kicks in, cosmological effect that kicks in at this level of precision. So I can point you to the reference.
Hmm.
Yeah, and actually people actually try to use it the other way. I mean, can we infer the peculiar velocity of the binary from this measured delay from the expecting one?
Mm-hmm.
I think that's more simple. We can use the ground-based part still to test VR, but to say that we will use it all the way up to these are the, it is hopeless because first of all, the ones that we are going to see in LISA are very close now, and secondly, they are seeing the frequency oscillations of thousands, not 10,000, like supermassive binary. So it's not really something that's super exciting for us.
It's not exciting.
Yeah, that is what I'm going to say. Because you can localize them very well. It doesn't matter if it's a few hours in that. You can see all those focus.
Sure, no. From the point of view of the text, it doesn't matter. From the point of view of testing GR.
Okay, I'm wrong. I'll take that slide out. Yeah, we're almost out of time. I will say briefly that I was alluding to the fact that you can combine multiple events, but this basically depends on having a common parameter that you can measure and you expect to be the same in all of your sources. So for the inspiral part, that's why we use this multiplicative difference in the phase coefficients, because you would expect it to be, well, if it's due to the presence of a fundamental field or something like that, then hopefully it would always be the same. That lets you then actually combine multiple events. We've started doing that even with the O1 results. So if you look at the 5914, the 151226 individually, you get these in terms of your parameterized tests. But then you can combine them together and you see that overall, if you take the two together, you're basically multiplying these two distributions together, then your tests get more accurate or closer to zero and also tighter. And that's because the heavier sources help at the high frequency, well, help at the late in spiral and ring down parts. So you can see 150914 has got better at this end than 151226. But 151226 is better at the low end because it lasts longer in bands. So these are tighter than that. So you get the benefits of both. And by measuring different signals with a range of different masses, then you tighten up these bounds all over the space of the PN coefficients. And that's just with two. You know, once you get more and more and more of these, the things will just keep getting better. Well, I don't think so. Yeah.
They are post-Newtonian coefficients, so it's a departure from post-Newtonian coefficients. These are all dimensional. The alternative, so in this, what is done is to change delta pi for each I separately, not all at the same time. I think a better test would be to change all of them at the same time, but we won't have sensitivity
Yeah.
for that in LIGO, but maybe in LISA.
We did do that actually. It's on this plot. The blue things are if you vary all of them, and it's just off the scale.
That's not very constraining. But there's no reason to change all of them, in my view, because no matter where the violation occurs, as long as it occurs somewhere, it will show up. It doesn't matter where you put that delta pi. After all, phasing is nothing but mathematics. That's my view. And it has been borne out by repeated confirmation of this.
This is just another way of doing basically the same thing. Rather than trying to constrain the error on those parameters, you can ask, can I detect a deviation? So model selection instead of parameter estimation. Here you get the results with a deviation in the 1.5 pn term. For single sources, it's, well, you can still probably make some detection of these things, the red being the violated ones and the blue being GR. But then by combining sources, you see that there's a much better separation because you're basically multiplying up the effect of getting different sources. So this is a technique that has been applied, especially by the NICEV group, to lots of different problems. First of all was me and Walter doing it for massive gravitons. Nice thing about this paper is the constraints that we predicted are basically the same as the ones that we measured with GW5914. So that was a very good result. And then also for ring downs and, well, the parametrized tests, and also for neutron star equation of state. If there's a common equation of state in all neutron stars, you can play the same game and pin that down as well. In the presence of a 10% violation in the 1.5 pn term. Yeah. No, it has to be the same. So this is really a common feature of all sources in that case. So it can't depend on the mass. It's dimensionless, so it shouldn't depend on the mass. It could depend on the mass ratio. Yeah. Right, I'm going to finish up. So LIGO and LISA, well, you've poured cold water on this slide already, but we can talk more about that tomorrow. So basically, to summarize, this is a completely new area of observational astrophysics, and so far, Einstein's still holding up very nicely. I personally expect that will remain the case for a good while, but it's important to test, otherwise we won't know if that's the case. The future, in the next few years, we're going to see more detections of binary black holes at higher SNRs that will give us better precision and better constraints by multiplying up different sources. Looking farther forward, well, first of all, we'll see different types of sources. We'll see binary neutron stars, hopefully. There you get into the sort of very long signal regime where you get better constraints at the low end of the post-Newtonian order. And you can start measuring matter effects in the waveform as well. And then once we get LISA flying, then we'll have this kind of multi-band gravitational wave astronomy, and I'm pretty sure that that will open up a range of different applications that we haven't even really thought about yet. So hopefully we can do some brainstorming on that in the session on LISA. So in terms of tests of general relativity, we're going to have a very busy time over the next few years trying to pin these down in different directions and looking at specific theories versus the generic constraints that we have. So this is a very exciting thing to be involved in at the moment, and there's plenty of good work to be done, not just in actually extracting the results, but in looking at where we can trust the models and so on. So that's basically it. I have a few discussion topics, but as I pointed out at the very start, even with LIGO, we're still sitting here. We've got a long way to go before we get into the sort of regime that we ultimately care about, which is whether gravity breaks down at the Planck scale or whether it's somewhere in the middle. If there are really additional fields that come in, then the energy scale for that could be somewhere lower, which would be helpful. But if we think that GR is correct all the way up to the Planck scale, then we're really hoping for any kind of lower energy phenomenon that is implied by a particular deviation at the high energy scales. So I haven't really said anything about what could happen up here or how it will affect things down here, but many of the theories that are in this generic tests are kind of low energy limits of different ways of looking at high energy gravity, like string theory and so on. That's way beyond my area of expertise, but it's a fun thing to speculate about. So I invite speculation to begin now, although we run out of time, so maybe we better stop. Okay, that's about it.